It is nice and stormy outside right now, so naturally it's a wonderful day to stay inside and read a book. I started this channel with a similar philosophy to the subtitle of this book. Big Ideas Simply Explained. I wanted to find out what I could about topics I'm personally interested in, and I think the challenge was for me to be able to distill information into a very accessible, obviously relaxing way as well for you guys, because that was mainly how I consumed most of the information that I got. I loved lectures, and I began falling asleep to them, and so that's why I'm so interested in this book, and it's very well done, the astronomy book, Big Ideas Simply Explained. And when I found out they have a whole series of books, I had to hop on Amazon and buy the science version of this book. Alright, so here we are. This book is chronologically oriented, and I'm a huge fan of looking at things in the context of their, of their history, of their social, technological, political contexts. And this book is much like Will Durant's The Story of Civilization and Story of Philosophy. It's a very well written account of these discoveries, because we ourselves are in a historical age. We call it contemporarily the information age, the internet age. For being wider, I guess we might call it the third industrial revolution. But it's helpful, I think, to attach yourself to the grand narrative of the human species and to live your life in the most meaningful way, I think, is to do the best good for simultaneously yourself, your family and friends, your community, and your species, ideally. So, to understand the status of everybody, not just your local, group of friends, is to have a good grasp on the history of the world and how we got to where we are, and the trajectory of where we're going. And science is a huge player in that. Science has given us, I found my sister, speaking of her, I saw her 6-year-old photo. But my little sister used to have an LG Rumor, and it's got all the buttons, no touch screen. This might have been right around the time the iPhone came out, but 1.3 megapixel camera. Cameras are about 12 megapixels now, regularly. I used to love. It had a really satisfying snap, which is very nice. Anyways, it's changing through YouTube, the internet in general, technology, how we communicate, the device you're probably watching this on right now, being a phone. It's revolutionized. I think I heard Jordan Peterson relate the Gutenberg revolution to today's internet revolution and podcast, the proliferation of audiobooks and podcasts and things like this, video forms. For Christians in the 1500s, Gutenberg, before he invented his brilliant interchangeable printing press to mass-produce books, people were widely illiterate because times were much harsher. Certainly weren't as many books just laying around to be accessed, because each one was hand-written, hand-copied, and of course prone to errors, with humans being the medium through which books were copied. And when you have one person who's literate as a pastor or an evangelizer telling a whole crowd in the form of story and spoken word, information's naturally going to be distorted and biased. But then with the invention of the Gutenberg press, people had much more available access to books, and therefore they became, generally, after a couple generations, much more literate, and were able to look, at the Bible or whatever the book of highest value might be. They were able to look at the source and make up their own minds and start to think for themselves, and not just be swayed by oration and great rhetoric. And what I'm trying to get around to is that people can consume content much more quickly now that they have access to information, and it's different than being subject of one person's interpretation in a small village in Germany in the 1500s, because we have access to millions of videos at least. And so generally, the less interesting, the less educational, the less, hopefully, scientifically, logically, historically truthful gets weeded out, and the most effective forms of communication remain. I think it's interesting. It's a very new medium. YouTube is extremely revolutionary. It gives people access to big ideas, ideally on my channel, simply explained. So I want to dissect this introduction to this book. It starts with: science is an ongoing search for truth, a perpetual struggle to discover how the universe works that goes back to the earliest civilizations. Driven on by human curiosity, it's a natural inclination for us to explore the unknown and ideally harness it for curtailing any human suffering that we might be able to with the new knowledge. Driven on by human curiosity, it's relied on reasoning, observation, and experiment. The best known of the ancient Greeks was Aristotle. He wrote widely on scientific subjects and actually laid the foundations for much of the work that has followed since. He was a good observer of nature, but he relied entirely on thought and argument, and he actually didn't do many experiments at all. I remember in Will Durant's The Story of Philosophy, he actually says that Aristotle made one of his many mistakes as a guy who took on such a vast scope of topics to explore would naturally make, was that women had a different amount of teeth than men. This book says one of the things he got wrong is he asserted that big objects, for instance, fall faster than small objects, which seems to make sense. If one object's weight is twice the other object's, you would think it would fall twice as fast as Aristotle did, but of course, 1600 years later, Galileo disproved the idea in 1590. Yeah, Aristotle was the 300s BC, so almost 2,000 years later, I guess. While it may seem obvious today that a good scientist must rely on empirical evidence, repeated experiments, it wasn't always apparent. And this is an interesting point that this book starts off with, to show that verifying things objectively through experiment and repeated experiments to assure that they aren't just one-off results wasn't always an instinctive, wasn't a common sense idea. You know, it took trial and error, and it took slow development of the faith in scientific experiment, if you will. So the scientific method, as we understand it today, was actually developed by a person. You know, it almost seems, again, intuitive. Like, okay, you make a hypothesis, you maybe observe something, get an idea of how it might work. You make a more detailed guess at how it might work by explaining out possible mechanisms, and then you flesh out how you might be able to test whether those mechanisms are true, whether they actually exist in reality. And if you can prove it with math and repeatable experiments, then you've made a point to establish a scientific theory. You've verified your hypothesis, and until it's disproven, you've been able to establish some sort of, at least if anything, temporary truth about the world and how it works. So a logical system for the scientific process was first put forward by the English philosopher. Again, interesting that it's a philosopher. That's the first intimations of, like, Kant, one of the greatest philosophers in general. He made speculations that ended up being mostly right about the cloud, nebula-like structures in the galaxy that most people thought were just close as all the other bright stars around us were actually, he said, he speculated at least, they were galaxies much further away, themselves composed of stars, being island universes. So the scientific method was put forth formally in the early 1600s by the philosopher Francis Bacon, who himself actually had I think it was like 300 years before him. Roger Bacon was a very famous proto-scientist, philosopher, if you will. So the Bacons had 6 degrees of influence and connection to the world around them through science way before Kevin danced onto the scene. That was really cringy, I'm sorry guys. So building on the work of the Arab scientist Alhazen 600 years earlier, who is a very accomplished scientist, and soon to be reinforced by the French philosopher René Descartes, who came up with Cartesian coordinates x and y. Bacon's scientific method requires scientists to make observations, form a theory to explain what is going on, and then conduct an experiment to see whether the theory holds true. So, if it seems to be true, then the results may be sent out for peer review, in which people working in the same or similar fields are invited to pick holes in the argument, and so falsify the theory. Or as Nietzsche said, again, it's interesting to make connections across hundreds of years and even millennia in some cases. Nietzsche, like Carl Jung, even though they're very interested in myth and story and religion and morality, things that we can't get a firm, tangible, observable grasp on. One of his famous phrases was, if it's unstable, if it's unstable, knock it over. He didn't want to believe in anything that couldn't withstand severe scientific scrutiny in the same rigorous spirit of Francis Bacon here. So he said he wanted and encouraged people to test his theory and perform similar experiments to make sure that they are able to be repeated and remain truthful across all domains of inquiry. He wanted to find truth, and interestingly, the Christian, one of its fundamental moral values was truth, was seeking truth and communicating truth through the spoken word. And if it was false, it was evil, and you can imagine there would be a correlation between the deeply, deeply Christian European culture and this pursuit of truth across the centuries. So that's something I'm still very ignorant about, the connection, but it's a tenuous one maybe, but at its at first sight, at least, it seems to make a lot of sense. Making a testable hypothesis or a prediction is always useful. English astronomer Edmund Halley, observing the comet in 1682, he realized that it was similar to comets reported around 1531 and 1607, 78 years later, and suggested that, now remember this would be deduction. There's induction and deduction, and it's taken me a long time to wrap my head around the exact definitions of these. But deduction would be, in this example, of deducing that, well, I just spent a half hour looking up different definitions of deductive and inductive logic in the true spirit of the channel. And I was reading a book on a history of ethics, and I was talking about Aristotle, and I could have sworn I had a good understanding of the distinction between those two. I guess I didn't, because, so I was thinking deduction was the standard phrases from the general to the specific, and induction is the specific to the general, but I guess a more accurate perspective would be that deduction is using multiple things, multiple truths that you've already pre-established as irrefutably true, such as 1 is a number, and 2 is the sum of 2 sets of 1, of having 2 ones, and therefore 1 plus 1 must equal 2. It's 2 general truths using a syllogism, relating, using the relation of, defining the relation of 2 objects based on a common relation to a third. And then induction would be, apparently, deduction gives you absolute certain truths, and induction gives you only probabilities of being true, because, and that's where the whole reasoning from the specific to the general comes into play, because it's, I guess the idea is that in induction you only have a few sets, and you have an incomplete set of data points that are insufficient to conclusively prove a point, but you can infer and induce a conclusion that's probably true if you make enough correlations between the sparse sets of data points. So it seems to be kind of like trying to prove your theory. I saw one other answer that induction essentially is a feature of the human language and can't be thought of as separate from it, whereas deduction can be something more like mathematical truths that most people assume would hold true regardless of human existence or not. So anyways, I thought I had some big idea easily explained. Apparently not. Any of you philosophy majors or just more intelligent people than I, maybe you guys can help me clarify the distinction between deductive and inductive. That would be a huge help for me. The main example, a famous example used for deductive logic, which is supposed to be using two separate universal truths to deduce a irrefutable third truth. All humans eventually die, or in other words, all humans are mortal. Second truth is Socrates was a human. And the third truth deduced by relating the first two, humanity means death, Socrates is part of humanity, therefore Socrates will eventually die. Those truths are found, they had to have been at some point arrived at inductively, I think, by saying, I'm noticing a lot of people dying, and so far I haven't found any person that hasn't died. So therefore I'm going to make the logical step and claim as a irrefutable, incontrovertible truth that all humans must at some point die. And then Socrates was a human. That's another thing that has to be kind of induced, by saying Socrates exhibits all these features of other people I define as human, therefore he must have been human. I'm having a real hard time understanding how that non-mathematical truth is deductive if it relies on inferences that are, we all know commonsensically, yes, all humans do die, and Socrates was certainly a human, but if we're really being rigorously logical about this, rational like a Vulcan, we could say there is some room to say maybe all humans don't die, maybe only most, maybe there is one human, like in the movie, one of my favorites, The Man from Earth, who lived 14,000 years and have yet to die. So, and maybe in the future humans won't die, so maybe that's not a universal truth. That's the reason why I got confused there. Anyways, that tangent's over. So Edmund Halley predicted that it would return, and he was right. In 1758 it did return. It was spotted on December 25th, and ever since, I guess he guessed the year, and it was 5 days short of almost being in the next year, so he looked out, and because his prediction wasn't that specific, it was almost wrong, technically. But ever since, it's been known as Halley's Comet, or Halley's. Astronomers are rarely able to perform experiments. Evidence can come only from observation for astronomy. Experiments may test a theory or be purely speculative. When the New Zealand-born physicist Ernest Rutherford, the famous professor at McGill, scientist, watched his students fire alpha particles at gold leaf in search of small deflections, he suggested putting the detector beside the source of alpha particles. And to their astonishment, some of the alpha particles bounced right back. And Rutherford then said it was as though an artillery shell had bounced back off tissue paper. And this led him to a new idea, to speculate the structure of the atom was the mass of the atom that he knew from scientific experiment. He just didn't know the placement and volume of the mass within the known volume of a total atom. He found that the mass was concentrated in what we now know as the nucleus, which is, you've seen those videos. If you think of a football stadium, I think the nucleus is something like the size, very roughly, of a basketball, or a soccer ball. And that's insane ratio of volume from the outer electron all the way to the nucleus. And that's a ridiculously, maybe non-intuitive thing that he was able to look at a bunch of evidence and, I guess, deduce. And as we're about to get to, that deduction is what most science is founded on. Those types of inferences, deductions, tests, and experiments. Experiment upon experiment. Until it either, continually gets buttressed and fortified with further, more extensive experimentation to continually support the theory, or extensive experimentation that eventually anomalously disproves it, such as the theory that all swans were white, and until, this is a famous case, until black swans were observed in Western Australia, that theory was considered universally true. We didn't think swans existed off of Earth, and we assumed all swans were white. And then yet we had to, obviously it's not a profound theory, so it wasn't that difficult to relinquish, but it's a good point that proves some of the things we take as irrefutably making sense and just true without any necessary further explanation. Those things sometimes can be false without us even having any prior reason to think they would be. So yeah, anyways, that's a famous black swan theory or hypothesis. So an experiment is all the more compelling to a scientist if the scientist, while proposing a new mechanism or theory, can make a prediction about the outcome. And I guess this is kind of like deduction. If this experiment produces the predicted result, the scientist then has supporting evidence for the theory. And even so, a scientist can never prove that this theory is correct. This is the really interesting part. As Karl Popper pointed out, is a philosopher of science. So he tries to understand science, tries to understand the limits of science, I guess. He says it can only disprove things. And that's an interesting reoccurring, that's another one of many things that reoccur when I'm reading history or science or philosophy, religion. It's hard to say what's true, because again, we're only humans, and we only have so much ability to be different places in the world and gather data for ourselves. But we know certain things aren't true, so we can't make universal claims of truth. A lot of times that's, in a way, I guess that's where our social nature kicks in, because we rely on communication with others to validate, confirm, substantiate our own ideas and perspectives and actions even. So, we something might be true locally, but not universally. We might have a incomplete truth, maybe. It's just interesting, the approach of truth from a standpoint of continual negation of or continual verifications of untruth. So you don't exactly know what true is per se by itself, but you slowly chip away towards it by identifying untruths, things that you know are not real and enduring in the natural world. So Karl Popper pointed out, science can only disprove things fundamentally, and that's so interesting. Every experiment that gives predicted answers is supporting evidence, but one experiment that fails may bring down an entire theory. So it's a really interesting one that I just looked up. I think it was off the University of Miami website. Was that a fisherman who might have been crossing the Bering Strait, 30,000 years ago, he might have had experience with multiple different bodies of water, maybe some sea, maybe the Caspian Sea if he was a really well-traveled person, some lakes and things like that, multiple other bodies of water before he hits the Pacific Ocean. And in his experience, all bodies of water he's ever come across, rivers, streams, lakes, all bodies of water have fish. Now he's decided to take a net and, in the same way he did with all the other bodies of water, approach the Pacific Ocean in the same way, with scooping a big net in the water. But he doesn't catch any fish. And he does it again and again to no avail. So after doing it 100 times over a couple weeks, let's pretend he has access to other food, he decides that because he has yet to catch fish, the theory that there are no fish in the Pacific Ocean must be true. And there's multiple ways you can word that. You could say that he has a theory that there are no fish if he doesn't catch any. And that's inaccurate, because that's not taking into account the reality of his small stature relative to the enormous, orders of magnitude much larger volume of water that is the Pacific Ocean, and his inability to access the fish that might still exist in the Pacific Ocean. This is something that I always had trouble with in statistics. He has a hypothesis. There are fish in this new body of water, and this is a tool. So the word hypothesis is something to be disproved or proven. An alternative or competing hypothesis would be that there are no fish in the body of water. So he wants to prove one or the other, and I guess logically that is a binary choice, because either it does have fish or it has no fish. To test the hypothesis, he sweeps a big net in the ocean. He repeats it hundreds of times and never catches a fish. Does this mean that the hypothesis, again, we take it as a unit so that we can easily manipulate it in our brain with words, is there are no fish in this body of water true? Well, we know that most likely it's not true. This is the essence of Popperian, Karl Popper, Popperian science, the essence of falsifiability in the Popperian theory of science. We know none of the explorers' hundreds of trials has falsified the no fish hypothesis. So the hypothesis, he can't disprove so far that there aren't fish hypothesis is true. Because so far it's proven to be true. But we know that there aren't fish in the Pacific Ocean hypothesis. Instinctively, we just know that's not true. But for this little experiment, it might be true that there are no fish. But just because he's dipped his net 100, 1,000, 1,000,000 times over decades and has never found a fish, we know that that doesn't prove that there aren't fish in the Pacific Ocean. So you see, this can kind of get a little messy, or at least complicated. I shouldn't say messy, it's actually logically concise. But Karl Popper, the idea that he's getting at, and again, this is important if you want to be a true scientist and have a scientifically oriented perspective. And it's good, I think, to be rigorously skeptical, about things. I don't want to just accept certain things on faith. I mean, something as innocuous as this example is not profound at all. But if we're getting into, things that might lead to something like the development of a phone or a cure for disease, I don't want to, on insufficient evidence, prematurely dismiss a theory. So none of the explorers' hundreds of fish trials have yet disproven that there aren't fish in the Pacific Ocean. To disprove that there aren't fish in the Pacific Ocean would be to catch a fish. The next trial might yield a fish. So we can't say that the phrase "there aren't fish in the Pacific Ocean" is true. We just say it's provisionally accepted, and that's the term that he uses. The falsification might still be out there. All it takes is the capture of one fish, and the "no fish, there aren't fish in the Pacific" hypothesis is disproven. So there's two more statements here. One is the explorer has not proven his "there aren't fish in the Pacific Ocean" hypothesis. He has not proven it, or provisionally found it to be true. Rather, the explorer, and here's a triple negative for you guys, the explorer has failed to prove there are no fish in the Pacific Ocean is incorrect. So what does that mean? That's a logically watertight way of saying that it's only provisionally true, but it could still be proven false. So we know that he's failed to prove it's incorrect. And that's how philosophers and logicians and engineers, scientists think. You have to leave room for the potential refutation of it in the future. So that's falsification and the philosophy of science of Karl Popper. And it's a very well accepted idea. Over the centuries, long-held concepts such as the geocentric universe, the idea that the universe was based on perfect solids and shapes like spheres and triangles and or pyramids and three-dimensional shapes and cubes. the four bodily humors, the idea that maybe the body is composed of things of a more spiritual nature. That was part of the idea that of bloodletting, or if you were sick, that just meant you had to be opened up and you need to let a couple liters of blood drain out of you, and then that's getting rid of the bad blood that's making you ill. The fire element, phlogiston, and a mysterious medium called ether that many scientists up until really Einstein, and it might even make a comeback with the concept of dark energy, but they used to think that is, rationally makes sense. Like a sound wave needs air and water, some sort of medium, metal, to travel through. They thought light needed a medium as well, but apparently it propagates in a vacuum of atomless, matterless voids. These in turn are only theories and may yet be disproved, although in many cases it's unlikely, given the support, given the evidence that the most prevalent, well-established modern theories are composed of. So now we have a fundamental outline of what is underlying the philosophy of science. Truth is the key concept in science. We want truth. We want to navigate through the world with a view as much in alignment with the most enduring aspects of reality that we know. And it's very interesting that science starts, fundamentally science is about making life easier for humans by knowing more about nature. But it has certainly evolved into a pursuit of nature for the sake of pursuing the unknown. There's many science theories that have no bearing whatsoever on human beings. So it's interesting how it can fork. And, we have medicine and maybe, the ideas of chemistry have been able to greatly advance our knowledge of how to assuage human suffering through chemistry and biology and physics and, machines that we developed for medical use. But certainly theories about galactic collisions on the scale of billions of years doesn't affect human lives in any way. So, science in that way can be amoral, but it's certainly, I think most people would agree that science might not be deliberately trying to reduce human suffering, but it's certainly, we know what it's not, and that's trying to increase human suffering. We know that's true. It's just interesting that fundamentally we can't separate how we ought to act from how things are in the world. If you're a human being who has to make choices and actions and move in the world, you have to make a decision about the moral value of what you're pursuing. So that's essentially the groundwork for modern science. That's originating in the pursuit of truth, the ruthless, rational, reasonable perspective on the world, not taking anything at face value, not taking, again, this is an ideal, it's not practically possible to do that. There's so many things like that. I won't get electrocuted if I, touch, my stove or an outlet because I have faith that whoever wired it did a competent job. We have faith in many things about the world. That my car won't just break down as I'm going 80 miles an hour down the highway. But ideally, science is about the pursuit of truth. And truth is it's a very powerful concept. Again, mainly because we know things aren't true. We know for sure. More often, we can be more certain about what's not true than we can about what is true. And that's helpful. It's helpful to experimentally verify, that pushing someone down is an untruth about how to act in a world in which as many people cooperate as often as possible over as long a time span as possible. And it's very cool to know that science fundamentally is ruthlessly trying to be objective, and it gets, like anything, it can be used for good and evil, but ultimately science itself has its roots, I would argue, in not a particular religion maybe, but a human instinct for good and the desire for the well-being, or at least the minimization of suffering for many people. And we, over the millennia, have gradually, increasingly become more and more adept species at being able to probe, pin, prick, unwrap, and peer underneath the layers of reality. And in order to find out about the nature of ourselves, we're all just thrown in this amazing experience that we call life. And nobody knows where it came from. We have the more recent steps down in geological and anthropological locations on Earth, in evidence, in bones, in fire pit remains, we can verify through carbon dating, and we have cultural artifacts from hundreds of thousands of years ago. We have so much information about the world compared to where we were, yet there's so many more questions now than ever before. But that's a good thing, because that means we're learning which questions not to ask and are insignificant, and we're learning many more questions that are very significant and useful and have a productive nature to them. And so it's science. More specifically, I'm interested in astronomy, but science in general is a very positive thing for the human race, because the more we know about the world around us, the more we know about ourselves, because we are part of the world. And it may not seem like it to you, and to me, I forget that I am sometimes, but it's a spiritual, it's a really deeply profound feeling to recognize that you're part of this black box that we're trying to deconstruct and understand the nature of. So it's the groundwork, the framework in which all this history of science lies and rests upon. Now, I love this next little paragraph because it's so beautifully put, and it nicely summarizes how science isn't random. It's very much built upon the preceding ideas of all the generations that come before us. Science rarely proceeds in simple logical steps. Discoveries may be made simultaneously by scientists working independently, as Leibniz and Newton and Darwin and I always forget his name. Wallace, that's what it is, Wallace. It's an interesting amount of incidents where a very profound scientific idea is supposed at and formulated at the same time by independent people within just a couple of years or even months apart in some cases. So I just had to quickly make a side note at how interesting that is. You know, from the calculus to evolution to the Hertzsprung-Russell diagram with the famous Danish and British astronomers independently coming up with the idea to classify stars according to their namesake. It's a very famous plot along which a vast majority of all stars nicely fit into. The reason most of those discoveries were made was not because of isolation, but in spite of it. It's no doubt that Newton and Leibniz, if they had been working together, maybe they would have, developed some, Riemann geometry or something much more advanced than the things that they did incredibly discover and invent on their own. And it benefits from the understanding of the most profound ideas of those that came before you. One reason for building the vast apparatus, for instance, known as the LHC, the Large Hadron Collider, was to search for the Higgs particle, whose existence was predicted 40 years earlier in 1964. That prediction itself rested on decades of theoretical work on the structure of the atom, going back to Rutherford, in the work of a Danish, Rutherford in his McGill laboratories, and the work of the Danish physicist Niels Bohr in the 1920s, which depended, of course, on the discovery further back, almost 30 years prior, in 1897, of the electron, which in turn depended on the discovery of the cathode rays, which in 1869. And we're not stopping there. We're continuing the etymology, the lineage of the LHC. And those could not have been found, the electrons in the cathode ray tubes, without the invention of the vacuum pump in 1799 and the invention of the battery. The vacuum pump came after the invention of the 1799 invention of the battery. And so the chain goes back through the decades and centuries. The great English physicist Isaac Newton, as someone corrected me, I thought I attributed it to Einstein, but it was Newton in one of my other videos. Newton famously said, "If I have seen further, it's only by standing on the shoulders of giants." And he meant primarily Galileo, because he probably also seen a copy of not only Galileo's works on the bodies of the heavens, I forget exactly what it's called, but no doubt he's probably had seen the Islam physicist, astronomer, intellect, Alhazen, that we mentioned earlier. A copy of his book titled Optics, because Newton was famous for having worked on not only lenses, but many ideas behind exploring the nature of light, such as how white light breaks into a rainbow pattern, spectral pattern. The first scientists, it's another interesting area, were the first philosophers with a scientific outlook were active in ancient Greece in the 6th and 5th centuries BC. Thales of Miletus predicted an eclipse of the sun in 585 BC. Pythagoras, we all know him, set up a mathematical school in what is now southern Italy 50 years later. And Xenophanes, after finding seashells on a mountain, reasoned that the whole earth must have at one time been under the ocean. In Sicily in the 4th century BCE, about 200 years later, Empedocles asserted that the earth, air, fire, and water are the fourfold roots of everything. He also took his followers up the volcanic crater of Mount Etna and jumped in, proclaiming that he wanted to show his immortality, and that's how we remember him to this day. So, the rigorous, well-defined, formal execution of the scientific method as we know it, as Francis Bacon developed it, wasn't fully fleshed out in the Greeks. It may have been, but as in just one of the examples of many of the works lost to history in the Great Fire of the Great Library of Alexandria in Egypt, we don't know how much knowledge about the ancient world was lost. And we don't know, therefore, of course, perhaps more elaborations on what science was to become. Meanwhile, in India, China, and the Mediterranean, people tried to make sense of the movements of the celestial bodies. They made star maps, partly as navigational aids, because of course, remember, most of this was, again, to help humans do things in the world. And they named stars in groups of stars. And just like all things we name, once you name something, it becomes a tool for you to use in the world. Squirrels, rabbits, foxes, dogs, and cats no longer become a blurry, nebulous indistinction of four-legged animals, but they become sharply defined categories that allow us to talk much more specifically and directly and potently about objects in the world and maybe how to manipulate them. If we need a pack of dogs to do something, or cats to worship in Egypt, I don't know. They noted that, these ancient peoples noted that a few stars traced irregular paths when viewed against the more fixed stars. The Greeks called these wandering planets, or wandering stars, planets. The Chinese spotted Halley's Comet all the way back in 240 BC. And in 1054, a supernova that we now call the Crab Nebula was spotted by the Chinese as well. In two famous quotes, one from Galileo, is that all truths are easy to understand once they're discovered, but the point is you have to discover them first. Rene Descartes says if if you would be a real seeker after truth, it is necessary that at least once in your life you doubt. As far as possible, doubt all things, at least once. In the late 8th century CE, the Abbasid Caliphate set up the House of Wisdom, as it was called, a magnificent library in its new capital of Baghdad. And this inspired rapid advances in Islamic science and technology, and many ingenious mechanical devices were invented, along with the astrolabe, a navigational device that used the positions of the stars to navigate. Alchemy flourished, which were the roots of chemistry. And really it is in the most, even though alchemy seems like a pseudoscience nowadays, it certainly wasn't, in its spirit, so to speak, was in the pursuit of truth about laws of nature that, certainly there's many things about nature that, like lightning, and, I can't help but think about that right now. I don't know, there's so many weird things in nature, especially random chemical reactions. The untarnishability of gold, I don't know any good ones, but alchemy wanted to understand nature, especially the mysterious, more microscopic interactions that ended up being chemical processes, and it evolved in the pursuit of knowledge before we were able to distinguish much more material things, characteristics of the world, from the vastly much more complex spiritual, psychological nature of human beings. Scholars at the library collected all the most important books from Greece and Rome, in India, and translated them into Arabic, which is actually how, and this is really interesting, I never knew about this, it's only through the Arab translations of these ancient Greek and Indian texts that modern Europe knows anything about the ancient world. So remember that. I'm sure there are exceptions, but certainly Greece was sacked and burned and conquered so many times after the great philosophers like Plato and Socrates and Heraclitus that the original texts didn't survive. And it's interesting that we now, revere those societies so much, but we only have a second-hand, maybe even third-hand account of the original texts, and they passed through the medium of Islam. So it's just an interesting fact of history. That's why many of, something like algebra, that's a very, very Islamic name. And there's many, many more examples that we just take for granted. We don't recognize anything with an AL in front of it. Alchemy, of course. What else would it be? Many stars. Aldebaran, I think. And of course, maybe the most interesting one of all that we owe to the Arabs, once we rediscovered their works, was the Arabic numerals. including zero, that the Greeks and Romans apparently never thought to use conceptually and mathematically. Okay, so I guess Arabic, or at least the concept of the number zero, was actually originated, as far as we know, in India. And the Arabs took that, and of course we received that knowledge maybe by conquering, maybe by taking it by force in the Crusades, but nonetheless we derive so much of our logic in mathematics and science and technology. All computers are a base 2 number system that is either 0 or 1. And any number in computer language is represented as an exponent of the number 2. And that is heavily dependent on understanding the concept of zero, I would say. The birth of modern science now, after we've seen it evolve from Aristotle and these ingenious, reincarnations, I guess, and translations and elaborations on Greek texts by the Arabs and Indians, and then the modern formalization of, okay, let's develop a system so that we can be as objective about the world as we undertake this thing we call science as possible. And there, in the 1600s, early 1600s, Francis Bacon derived that, and we use that as the cornerstone of what we view as the scientific method today. As the monopoly of the church over scientific truth began to weaken in the Western world, because of course the Catholic Church didn't want too much probing into the nature of the universe without attributing it to God. They didn't want to diminish their God in any way, so they had a very strict, they had a political, essentially a political theocracy, I guess, and a stronghold on the dissemination of knowledge for many, many centuries. And so as the Renaissance came and the trade increased and wealth, of course, increased as well, the general rising tide lifted all ships. People generally got more literate. In the 1400s, by the Gutenberg Press, knowledge started to become more valuable, more widely attainable as well, and more sought after by more people than ever at an increasing rate. And so the year 1543 saw the publication of two groundbreaking books. Belgian anatomist Andreas Vesalius produced De Humani Corporis Fabrica, which described the dissections of human corpses with exquisite illustrations. In the same year, Polish physician Nicholas Copernicus, I didn't know he was a physician, interesting. He published on the revolutions of the celestial bodies. I think it's translated as De Revolutionibus Orbium Coelestium, which stated firmly that the sun was the center of the universe, overturning the Earth's center geocentric view that had been modeled out by Ptolemy of Alexandria a millennium earlier, and of course made us perfectly in line with the idea that God created us to be the pinnacle of his divine touch. In 1600, English physician William Gilbert published De Magnete, which explained that compass needles point north because Earth itself is a magnet. And he even argued that Earth's core is made of iron. In 1623, another English physician, William Harvey, described for the first time how the heart acts as a pump and drives blood around the body, thereby quashing forever earlier theories that dated back 1400 years to the Greco-Roman physician Galen. In the 1660s, a couple decades, you can see we're moving decades by decade. We're getting more and more. The scientific elaborations and treatises and works and experiments and theories are expanding exponentially. In the 1660s, Anglo-Irish chemist Robert Boyle produced a string of books, including The Skeptical Chemist, in which he defined the chemical element as we know it today. This marked the birth of chemistry as a science, or not as we know it today, but it was certainly a prototype of the chemical element as an atom, as a fundamental unit. This marked the birth of chemistry as a science, and as distinct from the more mystical alchemy from which it arose. A guy who was very familiar with Isaac Newton, I wouldn't call them friends, maybe frenemies, Robert Hooke, who worked for a time as Boyle's assistant, produced the first scientific bestseller, Micrographia, in 1665. His superb fold-out illustrations of subjects, such as a flea and the eye of a fly, opened up a microscopic world no one had seen before. Then in 1687 came what many view as the most important science book of all time, Newton's Philosophiae Naturalis Principia Mathematica, commonly known as the Principia. His laws of motion and principle of universal gravity form the basis of classical physics, also known as Newtonian physics. So, I guess once Einstein overthrew it and modified it in great, so that it explained the universe in much more detail, much more accurately, in alignment with our increasingly accurate instruments, it was then we made a distinction between Newtonian or classical and Einsteinian physics. Again, moving on. In the 18th century, in the 1700s, French chemist Antoine Lavoisier discovered the role of oxygen in combustion, discrediting the old theory of the phlogiston that we talked about earlier, or briefly mentioned. I didn't say anything about it. Soon a whole host of new gases and their properties were being investigated. Thinking about the gases in the atmosphere, natural progression of ideas, you can imagine. A gas, it kind of feels like when you wave your hand through the air, one side feels, the front side, the side facing the motion, feels a little bit colder than the back side. Maybe gases are being compressed as you wave your hand through them. Perhaps that means there's some sort of similarity between gas, between air and water. And this led British meteorologist John Dalton to suggest that maybe each element consisted of unique atoms, and proposed the idea of atomic weights. Because if each element was made of different atoms, each type of gas was composed of fundamentally different particles, it would make sense that each of those particles would themselves have to be distinct in some way. And weight is a very, very old way of distinguishing, gold from silver or fake gold. The same volume of fake gold and gold are going to weigh different and tip the scales, so to speak. Then, on top of Dalton's works, the German chemist Auguste Kekulé, I pronounced that French, Kekulé, developed the basis for the molecular structure, while Russian inventor Dmitry Mendeleev laid out the first generally accepted periodic table of the elements. The invention of the electric battery by Alessandro Volta, of the guy whose namesake is Volts, in Italy in 1799 opened up new fields of science, into which marched Danish physicist Hans Christian Ørsted and British contemporary Michael Faraday. And they both discovered new elements and electromagnetism, which led to the invention of the electric motor, among many things. Meanwhile, the ideas of classical physics were applied to the atmosphere, the stars, the speed of light, the nature of heat, which developed into thermodynamics, which is very, very, very fundamental to so many different things. I mean, it's the nature of the dynamics of fluids and heat, how heat dissipates among different types of fluids like gases and liquids. Geologists studying rock strata now began to reconstruct Earth's past. Paleontology became fashionable as the remains of extinct creatures began to turn up. Mary Anning, an untutored British girl, became a world-famous assembler of fossil remains. With dinosaurs came ideas of evolution, because we have very large, very complex creatures that no longer exist, as far as we know. And then most famously Wallace and Alfred Russel Wallace and Charles Darwin developed new ideas on the theory of the mechanisms by which evolution might take place, and they suggested natural selection being one of them. So, in which isn't always the survival of the fittest, it's I heard someone say the other day, it might have been Eric Weinstein, the survival of the most necessary, the survival of the most, not adapted, but the most necessary organism for an ecosystem. That's an interesting idea. So if you're so well adapted that you're in symbiosis with other organisms, maybe your digestive system is indispensable for the fertilization of and propagation of other species. Maybe you act as a indispensable food source, or maintainer of a food source, and without you, your species and the ecosystem in which you are fully adapted would not thrive. So in that sense, you don't necessarily have to be the most fit. You have to be the most indispensable. Interesting idea. So moving into the 1900s now that we've established, theories of, anatomy and natural characteristics of the Earth, such as its iron core possibly, and making the compass needle move, and celestial navigation, noticing that some planets move and some stars certainly don't relative to them, the laws of gas and how different gases have different properties, how a lens of glass can open up to us a whole slew of ideas by analyzing microscopic organisms such as the cell, and maybe the lens created in a different way can open up to us the mechanics of the heavens, of those planets that we notice make different, but certainly consistently different paths as they orbit irregularly in the sky. And we have the idea of probing into the most fundamental ideas, the most fundamental elements of these different mediums, liquid and gases, and in this develops into the idea that perhaps we can deduce and dissect all of nature into some, a handful or a finite amount of definitely discrete fundamental building blocks. And in these ideas, we have very firm, logical, scientific theories, like Newton's, the epitome of which is Newton's Principia, in which he very eloquently defines laws of gravitation, and he develops the calculus, in which gives us so much of modern technology and science. And this just encourages more and more people. It's a feedback loop. If I was able to comprehend the Principia, I'm sure it's like an exhilarating feeling that you were probing behind some curtain you shouldn't look behind in the natural world. It's got to be amazingly exhilarating for these revolutionary, genius level thinkers in the scientific realm. In other areas too, spiritual and philosophical. I think organizing ideas in your mind to such a level that allows a clarity about the mechanisms of the natural world around you is a fascinating, rapturing experience. I vaguely felt notions of when I learned about these awesome ideas. When I was in engineering school, I would occasionally grasp at a fundamental level some of these ideas, and very occasionally, but when it happened, it's like, it's the most interesting, compelling phenomena to experience. It's like falling in love. It's like feeling a connection with someone. It's feeling a connection with a product of someone's imagination that perfectly explains the physical world, and that's a beautiful thing. So, at the turn of the 20th century now, we're in the 1900s, getting increasingly more complex. A young German named Albert Einstein, who was not German by the end of his life, by the way, because he was vehemently opposed to National Socialism, He proposed his theory of relativity, shaking classical physics and ending the idea of an absolute time and space. New models of the atom were proposed. Light was shown to act both as a particle and a wave. Another German, Werner Heisenberg, demonstrated that the universe was very uncertain with his principle about that. What has been most impressive, though, about the last century of scientific revolutions was how technical advances have enabled science to advance faster at an accelerated rate. Ever more powerful particle colliders revealed new fundamental units of matter. Stronger telescopes showed that the universe is expanding and most likely started at a single point in space. And the idea of black holes began to take root, where Einstein's equations inevitably lead to the entities composed of matter on the scale of thousands to millions of times more massive than our sun, celestial bodies that have more mass and are made up of more matter that give them that mass, to such an extent that they are tens, hundreds of thousands to millions of times more massive. They have that much more mass than our sun. They're fundamentally unstable. They don't create a billion or 4 billion year long balance of internal nuclear outward nuclear fusion based outward pressure from the inside balanced perfectly with an outward pull from of gravity, outward pressure directed inward of the gravity created by such matter. A nice, beautiful, billion-year-long balance is impossible with objects beyond a certain mass, located in a certain small enough volume of space. And Einstein's equation said a collapse will happen in a singularity, meaning, I think it's when you divide by infinity in math, will happen. And somehow we've been able to look and probe in our own galaxy filled of billions of stars. We've been able to see that there are stars that orbit at a very fast pace, a point in space that has no light. So we can see light, visibly luminous objects we call stars, orbiting a point in space that itself, as far as we can see, has no luminosity. And although it could be a very tightly packed group of small stars, just many of them to equal that amount of mass that would make other stars orbit them that fast, it's probably not, because I just heard this the other day. We would be able to detect a wobble in the spectral emissions of the stars as the gravitational force exerted on them by a star cluster would vary by small amounts as it got closer and closer to this unevenly distributed series of masses, gravitational entities. So in other words, we would be able to detect a slight wobble of this star's orbit around a a series of a star cluster because it doesn't have a tightly defined single concentration of mass. It would be a loosely spotted series of gravitational effects making these stars orbit it. And so we know, we don't know, we have faith that our science is most likely right in being able to speculate it's a black hole, it's a singularity in space that would have to have the mass equivalent to 4 million suns if it's able to gravitationally bind all of the stars that we see orbiting it. And so dark matter and dark energy, whatever they are, seem to fill the universe. Astronomers began to discover new worlds, planets in orbit around distant stars. We call them exoplanets. Some of which, I believe many of which, probably harbor life. The British mathematician Alan Turing thought of the universe as a computing machine. And within 50 years we had personal computers. Within 50 years. World Wide Web, smartphones. Now we got Elon Musk trying to put filaments on the orders of hundredths of the width of a human hair in our brain to increase our cognitive abilities. It's just bizarre and scary. In biology, chromosomes were shown to be the basis of inheritance, and the chemical structure of DNA was finally decoded. In just 40 years, this led to the Human Genome Project, which seemed a daunting task in prospect, but yet aided by computing, it got faster and faster as it progressed. DNA sequencing is now an almost routine laboratory operation, and gene therapy has moved from a hope into a reality. And the first mammal has been cloned. As today's scientists, to wrap this up, build on these and other achievements at an accelerating rate, the relentless search for truth continues. It seems likely that there will always be more questions than answers, but for future discoveries will absolutely continue to amaze and, with any luck, help humanity flourish, and along with a great diminishment of suffering in the world. That's why I love Star Trek so much. So that is the science book. That's the first 2 pages. Somehow I spent 3 hours recording this. Probably going to be about a 2-hour video. I hope I wasn't rambling too much. I'm just so fascinated in the not only the content but the history and the context in which the content was thought up, discovered, in some circumstances even dreamt up, imagined, and it's a force to be reckoned with in the modern world. And if we don't have a good enough appreciation for science, at least we're not going to be able to utilize it to its full potential to do the miracles that it has the potential to do. And at most, we might unknowingly make huge mistakes with the power that it grants us. So I really feel like being technically proficient is probably a really, and not just technically, more so intellectually rigorous. Being trained in that, in understanding how to ruthlessly critique and analyze rationally arguments, using evidence, using, intuition to approach, to discover things about yourself, and to explore with an inquisitive and skeptical mind. That's, I think, what I enjoy most about learning the history of science, and what effort and what hard-won, or what the lives, these people gave up in many circumstances has amounted to. And it's encouraging to know that, yes, there may be people smarter than you out there, but we all need each other in a fundamental way. I mean, we might have been 1,000 years ahead technologically where we are right now if we hadn't disintegrated and lost so much of what I'm sure the Roman world and Greek world and other ancient world civilizations had to give us. And with any luck, YouTube and the modern internet information age, the third industrial revolution that we're a part of, will do nothing but help advance the communication of truthful, or at least not false, information that aims to make each individual a more knowledgeable, but also a more skeptical and intelligently critical human being in the world, because we're all centers of unimaginable complexity in our brains. We have so many connections going on up here that to manifest their full potential would be an amazing sight to really see. They have 7-8 billion people living up to their full potential would be truly heaven on earth. I think science is going to be a key player in that, if that ever happens. So, as always, thanks for being the encouragement that I need to make these videos continually. Thanks for watching. Sleep well. I'll see you next time. Bye.